This is the next version that DeepMind company revealed, and it is much better than their previous version. It's more general than that. It is also published in Nature because it's important. My research interest is at the intersection of reasoning, especially memory-based reasoning, and semantic parsing, and knowledge base. Because when you use Hopfield network, it has a associative memory in your hippocampus. So it's very interesting when it converges to stable fixed points, and it converges to some patterns that you have in your mind. Knowledge base is an important part of your brain, and also in modern algorithm for reasoning. For semantic parsing, there are many ideas, like, for example, I like AMR, abstract meaning representation. So I want to explain this article in 2016 in Nature by DeepMind company, and Demis is the CEO of the DeepMind company, I guess. And Alex Grave, I introduced him in the previous lecture. So we are implementing, we are talking about this hybrid computing. And there are other articles that are interesting as well. For example, this one is really beautiful, differentiable memory. And so what is the problem of deep learning? It has lack of external memory. Artificial neural networks are remarkably adept at sensory processing, sequence learning, and reinforcement learning, but are limited in their ability to represent variables and data structures and to store data over long time scales, owing to the lack of external memory. Another problem of deep learning is that it has lack of memory allocation ability. As the memory demands of a task increase, these networks cannot allocate new storage dynamically, nor easily learn algorithms that act independently of the values realized by the task variables. In our brain, how can we allocate new memories? When we are asleep, there is a process between your hippocampus and neocortex. Because hippocampus, for example, they're just very short-term memory. If you don't sleep, it cannot understands how to pay attention, how to store it in your unconscious mind, which is at the neocortex and higher layer of your brain, and so you cannot store it in your brain. And we allocate memory in our brain in a totally different way than we do in our computers. So what is a differentiable neural computer? We introduce a machine learning called the differentiable neural computer, which consists of neural network that can read from and write to an external memory, just like the previous lecture. It is analogous to the random access RAM in your conventional computer. Of course, cache is much faster than RAM. So we connect cache to RAM. So cache is more closer to your CPU. It's like regions of your brain. They are connected to each other. When, for example, they are closer to something, it means something more important. It means it is the priority that this arrangement is like this because of their speed, their kind of neurons that they use, and many other things. So we draw inspiration from this biological fact. When trained with supervised learning, we demonstrate that a differentiable neural computer can successfully answer synthetic questions designed to emulate reasoning and inference problems in natural language. We show that it can learn tasks such as finding the shortest path between specific points. Oh, we have done this in my playlist for Hopfield Network. We use the energy, we designed energy for shortest path, also for 8 queens, also for 8 rooks. Those problems we solve it with designing a Lyapunov function such that when the energy of this Lyapunov function is reduced, the state converges to the solution of your problem. So interesting. A DNC is a neural network coupled to an external memory matrix. The behavior of the network is independent of memory size as long as the memory is not filled to capacity, which is why we view the memory as external. So this is the differentiable neural computer architecture. It has write vector, erase vector. It has input and output, just like the previous lecture. This is their controller, which I call it CPU. They call it controller. And this is the memory, because we need to read and write to this memory, which is n by w dimension. And they have memory allocation issue here as well. Whereas conventional computers use unique address to access memory contents, a DNC uses a differentiable attention mechanism to define distributions over the end rows or locations in the memory matrix. These distributions, which we call weightings, represent the degree to which each location is involved in read and write. So this one is like the previous lecture. W is those things that I said, the sum to 1 and is softmax of something. It's like soft attention. So the idea is, until here is everything is the same as previous lecture, neural Turing machine. So what is the system overview? A recurrent controller receives input from external data source to produce output B and C. The controller also output vectors that parameterize one write head green and multiple read heads. The write head defines write and erase vector. So there are 3 forms of differentiable attention. Interaction between the heads and the memory. The heads use 3 distinct forms of differentiable attention. The first is content lookup that I explained in previous lecture, in which a key vector emitted by the controller is compared to the content of each location. The similarity scores determine a weighting that can be used by the read heads for associative recall, or by the write head to modify an existing vector. So these articles are about key value memory retrieval. I've explained some of them in my YouTube channel. For example, I've explained this one. I think I've explained this one as well, because I like all of the articles of Christopher Manning. I like to explain all of them. So there are 3 forms of differentiable attention. A second attention mechanism records transitions between consecutively written locations in an n by n temporal link matrix. So L of ij is very interesting. It says that L is close to 1 if I was the next location written after J, and it's close to 0 otherwise. So it measures the temporal structure, the temporal things, the priorities, that which location is written first. First this location, then you go, for example, this is a memory, first this location, and then you go here, then you jump here, then suddenly you access here. It records all of them. And because it's a matrix L from I through to the J's column, you can understand any combination, it's just like a probabilities in Markov chain. If you know the transition, you know everything. You know the dynamics of everything. So you can replay and go and simulate all of those behaviors and trajectories. The third form of attention allocates memory for writing. The usage of each location is represented as a number between 0 and 1, and a writing that picks out unused locations that is delivered to the right. The design of attention was motivated largely by computational considerations. Remember human free recall? I have an article about this, how your hippocampus and neocortex implements these things. I have 3 articles about hippocampus in my Medium website, medium.com, and it's very interesting. I'm very excited about that human brain is more efficient than our computers. Synthetic question answering experiment, they used this and I like this data set very much, BABI data set. It's like, for example, John goes here, drops something, and now where is the bag? So it's like a story. I like it very much. And so you need to have memory, because at different stage, you are at different context. So you should understand something, for example, where the bag is at each stage. So that this is the path for your reasoning. And so this data set is amazing. But it's very simple data set, because simple sentences, subject, verb, object, so very simple. You can represent it by a knowledge graph. It's very simple. And these are experiments that they did. For example, this one is very simple. So their data set is very simple. How can we understand the challenge if the data sets are very simple? Why are number of reads at each time step? This is an important question for me. Our brain is asynchronous, but the computer architecture, everything is synchronous by clock. And before being used to parameterize the memory interactions, the interface vector is subdivided as So this is the idea that we used in the previous lecture. We know content-based addressing from previous lecture is just softmax, soft attention. And they do an interesting thing, dynamic memory allocation, which I still don't know why they use this law. I still don't know. It's very mysterious. I still have many problems with this article, but I appreciate the L definition of L, the degree to which location I was written to after location J, because they use L to update that at the next stage. They can keep track of the locations of that are written or read from the memory, so that you can replay later.